So, hi everyone, my name is Olivia Su. I am a fourth year PhD student co-advised by Fred and Kunle Olakun. I will be talking about the Sparse Abstract Machine, which is a way to represent sparse tensor algebra as streaming data flow graphs. So similar to using accelerators in dense tensor algebra, many people have been looking at sparse data flow accelerators for sparse tensor algebra. And this can be seen by the increasing number of architecture and accelerator papers that have been showing up in the recent years. And hopefully I don't have to convince you of this, since previous talks in this session have demonstrated the importance of sparse applications and sparse tensor algebra. However, we need generality because there are many different sparse computations that users want to do, including the long tail of expressions, not just SPGEM. And unlike the dense tensor algebra, which can be reduced to matrix multiplication efficiently, sparse tensor algebra cannot in general, because this will significantly impact the performance, since factorizing into sparse matrix multiplication calls can lead to asymptotically worse performance, as shown by prior work, including the Taco paper. So therefore, the current obstacles with developing a fully general sparse tensor algebra system over its dense counterpart is mainly attributed to the large space of sparse computation. And so what do I mean by this large space? So a fully general system must include the long tail of expressions that I previously showed, backend specific and optimizing transformations, also known as schedules, various compression structures, which previous talks have talked about, but I'm not going to show here or emphasize. And additionally, this leads to further complexity in the actual number of prior work backends that currently exist, as well as the ones that can be built in the future. And this large space motivates the need for a compiler from sparse tensor algebra to sparse accelerators. To further demonstrate the importance of a system that can handle arbitrary schedules or optimizations, let's take a look at kernel fusion and data flow orderings. So here is sample dense matrix multiplication, or SDDMM for short. It is a kernel where a sparse matrix samples a dense matrix multiplication. And it's a kernel used in many machine learning applications. So here is the performance of the unfused computation, which is first doing the dense matrix multiplication and then sampling by the sparse matrix B, as well as the fully fused computation, which is highlighted in the bold black boxes, which shows only doing the dot product on the non-zero values of B. And we show that there's almost a 2 orders of magnitude speed up when you take into account the schedule of kernel fusion. Additionally, now let's look at sparse matrix multiplication, a very common expression used in sparse data flow accelerators. And I show all 6 sparse matrix data flow orderings. And again, we see almost a 2 orders of magnitude difference, depending on which data flow ordering is shown. So what this means is that the compiler system that we generate, that is general, needs to model and handle needs to handle fusion by default and arbitrary data flow orderings. Or additionally, what this means is that the architect, if they're trying to build a fixed function sparse accelerator, needs to actually search this space of data flow orderings and kernel fusion to then pick what is the best option for them before they harden their accelerator. So although I already motivate the need for a compiler, I kind of also want to mention one more thing, is that what we really want is a compiler with a clean abstraction interface. So as LLVM and ISAs have shown in the past, this clean interface will lead to simpler designs for the rest of the system. And what I mean by that is it will allow both the compiler to be designed and the hardware to be designed both independently and in parallel. So that is one of the big goals and motivating factors of our Sparse Abstract Machine as well. So not just a compiler flow and not just a design space exploration tool, but also a way to cleanly interface between your compiler and your hardware implementation. So therefore, we propose the Sparse Abstract Machine, or SAM. SAM is an abstract machine with infinite resources, so we assume that it has perfect memory, and we assume that it has single cycle computation, which is not true of real hardware accelerators. But this allows us to actually decouple the design of SAM from specific hardware accelerator implementations, and then SAM can then lower to those specific implementations. Our compiler that comes with, our front-end compiler that comes with SAM is called Custard, and Custard's input API is 3 high-level languages, the same as prior work from the original Taco. And additionally, SAM can act as that abstract machine or compiler IR, and then we show in our system that we can actually do 3 things in lowering. We can first bind SAM to a cycle approximate simulator that allows hardware designers to use it as a design space exploration tool. Next, SAM, we show, can harden to pre-existing fixed function accelerators. And finally, SAM can also bind to reconfigurable accelerators. So both reconfigurable dataflow accelerators, RDAs, and coarse-grained reconfigurable arrays, or CGRAs. So SAM is, like I mentioned, an abstract machine, and it represents dataflow hardware through 2 main mechanisms. The first mechanism is wires carrying data through streams. And the second mechanism is that are modules that compute on those streams of data through what we call SAM primitives. And these SAM primitives functionally have finite state machines in them, or digital state machines. And each SAM primitive can compose and can take any number of input streams and output streams. And then now I will give the details of the SAM stream representation. So SAM must actually represent these multi-dimensional tensors, especially higher order ones, as various flattened streams that are more suitable for hardware. So the SAM representation is able to transform multi-dimensional tensors to various one-dimensional flattened streams. And there exists one coordinate stream per dimension of a tensor plus a value stream. So together, a bundle of streams make up the representation of a single tensor. And the stream comes with non-control tokens like indices and values, and also have control tokens. So we have stop tokens and done tokens within the SAM streaming representation. The stop tokens denote the end of tensor dimension or rank, and preserve this is the shape and the multidimensionality of the tensor. And the done token represents the end of the stream. And then additionally, these tensor streams start out from arrays and then can be written back to arrays in memory in space instead of representing the data in time. So now a more detailed view of SAM primitives that perform computation. So SAM primitives are cleanly defined interfaces for each feature of sparse tensor algebra. First, we have level scanners, which compose to iterate through multi-dimensional tensors. So one level scanner can iterate through a single vector, whereas composing 2 level scanners, as shown, can iterate through a matrix. Then we have primitives that combine multiple tensors together or perform stream merging, and we have an intersector and a union, one for addition and one for multiplication. Then we have the repeater, which repeats operands over other operands. So this is similar to broadcasting, so similar to a scalar multiplying by a vector. And then we have the computation primitive, so standard ALU, and then also reduction operation support. And finally, we can assign multidimensional results back in SAM to memory. And this is it. These are really the only 5 features you need for sparse tensor algebra. And we make an argument for this in the Sparse Abstract Machine paper. So since our abstract machine can handle any algorithm in sparse tensor algebra and can handle many schedules, including fused and unfused and any data flow ordering. It is most similar to prior work on sparse reconfigurable architectures. However, prior work is missing various things. Some prior work on sparse reconfigurable architectures are missing representations for higher order tensors. Others may not support unions or additions. And then finally, some that exist are limited to what we call pseudo-sparse iteration, which is actually a proportionally dense iteration. So it's a dense iteration by some constant divided by some constant factor. And additionally, since SAM is an abstract machine, these prior work reconfigurable accelerators are actually considered implementations of SAM. So we show that SAM can actually implement kind of these prior work accelerators that are a subset of the domain. So coming back to the details of how SAM, now that I've explained how it's general and how prior work has limitations really works, let me give you a vector scaling example. So in this case, we have a vector B scaled by a constant C to show how the primitives and the streams actually interact together. So each zero element of B is denoted in gray, and each non-zero coordinate of the vector B is emitted as a stream by the level scanner. So, and it's color-coded, shown on the right. And the stop token denotes now the end of the vector B. And the done token, like I said, denotes the end of the stream. Now the scaling of the vector of the constant C is done via the repeater, where the reference of C, which is just a zero address, then gets repeated to every non-empty element of B, with again the control tokens denoting the same thing, the end of the broadcasted C value. And these references and coordinates are then used to compute the result and pass down to a later part of the SAM graph. So now that you kind of have an intuition of how the SAM streams and primitives compose together, I'm going to show this full SAM graph that composes for sparse matrix multiplication. The details are not so important, but as you can see, there's a region of the SAM graph that does input iteration and stream merging. There's also the computation, which is then actually computing the values you need to store back to the result. And finally, doing the tensor construction of the result. And the most important thing to note here is that actually most of the computation is done through input iteration and stream merging. And what that means is for sparse computation, which this is prior knowledge, but it's shown here spatially, that most of the work is used to filter out and compute on the metadata before you actually want to compute the values. And then, as mentioned previously, multiple times, SAM is abstract, but SAM can still be used to model real-world hardware. So what we will do is that we have the abstract SAM machine, but first we're going to take in an architectural configuration of a backend you want to model, and this includes real implementation values, including values of your memory subsystem in your architecture. And then in our simulation, given that architecture-specific information, like bandwidth and latency, we can use the SAM graph to sequence actually tiled data. So the SAM graph can be used to intersect the tile IDs to filter out tiles. And another SAM graph can be used for the inner level of the computation. And so given this full simulation flow, we actually show and we're able to recreate prior work performance numbers from extensor. So specifically, we were able to recreate this extensor's SPM performance across varying dimension sizes with a constant number of non-zeros, just using our SAM simulator. And the point is that even though abstract, we can actually use it to model pre-existing like finite hardware. So that's kind of all the stuff done on prior work, and then now we're using SAM and Custard to build new hardware as well. So here I show prior work CGRA called Amber. This was presented at the VLSI Symposium in 2022, and it was fabricated in TSMC 16 nanometer. It is a fully dense CGRA, so it does dense graphics and machine learning applications like camera pipeline and Gaussian blurring. And we're able to, with the addition of the SAM primitives, just a handful of SAM primitives defined, create and fabricate a new chip called Onyx in GF12 that is a CGRA that both has dense capabilities as well as sparse applications. So we can do sparse tensor algebra in addition to dense linear algebra, graphics, and dense machine learning applications. So how do we do this? Well, first we leverage compiling to SAM using Custard for the front end. So a user just has to write using the 3 high-level languages into the input of the compiler. And then it goes to concrete index notation, which outputs an iteration graph that is a spatial representation of, instead of a loop-based representation of the computation. And then our compiler Custard is able to map that to the input iteration space as primitives. And then now that we have the SAM graph in the toolchain for Onyx, and given our Custard compiler, we actually have a mapper to a reconfigurable dataflow accelerator. And then we leverage the Stanford Agile hardware flow to then actually place and route and also generate the bit stream for the coarse-grained reconfigurable array Onyx. And in addition, we use SAM and the cycle approximate functional simulator as a verification checker. So this allowed us to tape out just the sparse application side of the chip with just 2 people in a little over 4 months. In conclusion, we present SAM, a representation model and compiler IR for sparse tensor algebra as streaming data flow. We hope that SAM will improve future sparse accelerator usability through a compiler and representation that can target any hardware that you decide to design. And we also hope that it will improve future microarchitectural designs as a design space exploration tool for future hardware. And additionally, something a little hopeful, we would like SAM to inspire the development of abstract machines for other application domains as well, not just sparse tensor algebra. Thank you.